Okay, so we are very happy to have here today Nuno Santos, uh, that is performing his PhD at Instituto Superior Técnico in Universidade de Lisboa, in a joint supervision by Professor José Pizarro Sandi Lemos, Nico Sanches Gual, and Professor Carlos Alberto Ruivo Herdeiro. Nuno, from this moment on, the stage is yours.
Okay, so I'd like to thank not only Professor Luís Crispino for inviting me to your group meetings, but also those who have joined. So today I'll speak about black holes, stationary clouds, and magnetic fields. At least that is the title of my talk. So this particular work was done under the guidance of one of my supervisors, Professor Carlos Herdeiro, who I believe some of you already know. And it was published in Physics Letters B early this year, in April, I think. So I'll assume that everyone in the audience is familiar with the black holes and magnetic fields in general. However, I think that some of you may never have heard the term stationary clouds. And loosely speaking, these stationary clouds are bosonic field condensates in equilibrium with black holes. So during the next few minutes, I'd like to explain more precisely what these stationary clouds are and put you in the picture about their connection with black holes and magnetic fields, okay? So for that purpose, I'll start off by looking at some of the strongest magnetic fields in the universe. So as you might know, some neutron stars known as magnetars are highly magnetized. So they are surrounded by super strong magnetic fields and have an unpredictable burst period. This table shows or contains the surface dipolar magnetic field strength, B, of most of the currently known magnetars or magnetar candidates. I think they are 26 in total. So as the table shows, the strength of these magnetic fields ranges from 10 to the 12th to 10 to the 15th Gauss. For instance, this magnetar SGR J17452900, which orbits the supermassive black hole Sagittarius A star at the center of the Milky Way, has a magnetic field of 10 to the 14th Gauss. Okay, so this is an example. Well, the space-time curvature induced by a magnetic field of strength B is of the order of B squared. And on the other hand, the space-time curvature near a black hole of mass m is of the order of the inverse square of m. So as you can see, these two contributions are comparable only if B is of the order of the inverse of m. So this relation on the left sets a threshold value for B as a function of m. So a magnetic field of order BC or larger distorts, warps the space-time in the vicinity of the event horizon, but without changing its topology, which is important. So let's assign some values to the mass m of the black hole. For instance, this threshold value BC is approximately 10 to the 18th Gauss for a stellar mass black hole with 10 solar masses, and it's about 10 to the 10th Gauss for a supermassive black hole with 10 to the 9th solar masses. Okay, so since the strength of a magnetic dipole, as you might know from electromagnetism, falls off as the cube of the distance from it, it is very unlikely that a stellar mass black hole or even a supermassive black hole is influenced by such a strong magnetic field. Anyway, this is not our aim. So our aim is not here to discuss any particular astrophysical scenario. These estimates are only relevant to define the validity of some assumptions we'll make later on. Okay. So even if the strength of a magnetic dipole is significantly smaller than BC, which we'll assume that's the case, the impact of the magnetic field on a scalar field, for instance, interacting with a black hole may be non-negligible. So because the field can acquire an effective mass and be trapped or be confined to the vicinity of the black hole. So in addition, if the field is bosonic, as you might know, this field can induce superradiance, which is the extraction of energy and angular momentum from rotating black holes. And superradiance takes place when the phase angular velocity, can you see my pointer?
Yes, we can.
Okay, so superradiance takes place when the phase angular velocity or frequency omega of the field satisfies this inequality. So where m is the azimuthal harmonic index and capital omega h is the black hole's angular velocity. So together with a confinement mechanism, which can be a reflecting mirror, or it can be provided by a field with non-vanishing mass, the superradiance can be responsible for bosonic fields to form quasi-bound states. These quasi-bound states can be stable if they decay exponentially in time, or they can be unstable if they grow exponentially in time. So the later quasi-bound states, these are unstable. So these ones that grow exponentially in time are unstable and form what Press-Tukolsky called a black hole bomb. Okay, but something special happens when the field and the black hole synchronize. Okay, in a sense, when that inequality turns into equality. So when omega equals m times capital omega h. In that case, bound states in the true sense, so bound states with vanishing imaginary part can form. And these bound states were first found by Hod in 2012. Who named them stationary clouds. So these stationary clouds are nothing but real frequency states characterized by this synchronization condition. And much attention has been paid to these solutions since they were discovered by Hod, but most works rely on massive fields, so fields with a non-vanishing bare mass. However, a non-vanishing bare mass is not always mandatory. Okay, so the trapping of the field can be obtained when the field is massless, even as long as its effective mass is non-zero. For instance, as we'll see in a bit, a massless bosonic field interacting with a black hole immersed in a magnetic field is also likely to form these bound states, these stationary clouds, because the magnetic field confines the environment, okay? Confines the field to the vicinity of the black hole. Okay, so an example which naturally embodies this idea is the interaction of a massless scalar field with a Reissner-Nordstrom black hole immersed in a uniform axial magnetic field. And this black hole, this solution, if you will, is commonly known as Reissner-Nordstrom-Melvin black hole. I wrote RNM for short in the presentation, and it's a solution, it's an exact solution of Einstein-Maxwell theory. So this solution is not asymptotically flat, so it asymptotically resembles the magnetic Melvin universe. And I don't know if you are familiar with the magnetic Melvin universe, but it describes, how can I say, it describes a non-singular, so a regular, static, cylindrically symmetric spacetime, representing a bundle of magnetic flux lines in gravitational magnetostatic equilibrium. Okay, so loosely speaking, if you want a more not so formal definition, it's like having Minkowski spacetime immersed in a uniform magnetic field. But we always should keep in mind that such magnetic field, no matter how small or how weak it is, it changes the global structure of the spacetime, in particular the asymptotic behavior of the spacetime. Okay, but keep in mind that this spacetime is not asymptotically flat. Okay, so it is possible to embed, to immerse any asymptotically flat stationary solution of Einstein-Maxwell theory in a uniform magnetic field. And this can be done using or by means of a solution generating technique called Harrison transformation. Some people call it magnetizing transformation because it immerses another solution into a magnetic field. And this possibility was first realized by Harrison, and it was this transformation was applied by Ernst to the solutions of GR, so to the Schwarzschild black hole, to the Reissner-Nordstrom black hole, the Kerr black hole, and the Kerr-Newman black hole. Right? So you can embed all of these solutions in a magnetic field and obtain, using this transformation, an exact solution, which is convenient. So here's the metric G and the electromagnetic for potential or Maxwell field A for these black holes. So you can see that the metric functions, so delta, capital lambda, capital omega, they are rather complicated, right? Anyway, again, this is an exact solution. So capital M and capital Q are the mass and the electric charge of the black hole. B naught is the strength of the uniform magnetic field. And here we will assume that this B naught is much weaker than the threshold value BC that we defined some minutes ago. So this approximation will be important in a bit. Okay, so when applied to the Reissner-Nordstrom black hole, the Harrison transformation produces, as you can see, a stationary rather than a static solution. So here I have highlighted the dragging potential of this black hole, capital omega, and you see that it is directly proportional to this coupling Q times B naught, okay? Which suggests that the interaction between the charge and the magnetic field sources the rotation of the black hole, okay? And for those who are not familiar with these solutions, it might come as a surprise that this spacetime is stationary rather than static. But this is, if you think a bit, this is not, in fact, that surprising, because if a charge, if you think the following. So if a charged black hole rotates, or if you will, if a charged body rotates, it will induce a magnetic field. So you can think the other way around. So if an external magnetic field is applied to a charged black hole, the black hole will rotate. Okay, that's why we get this stationary solution rather than a static one. Okay, so let me remind that we are interested in finding bound states between a massless scalar field and a Reissner-Nordstrom-Melvin black hole. So for that end, for that purpose, we must consider the Einstein-Maxwell theory, minimally coupled to a complex, or it can be real, in fact. So let's say a real or complex ungauged scalar field, so a scalar field without mass and without charge. This is the action of such theory, and here we have the corresponding equations of motions. So the Einstein's equations, the Maxwell's equations, and the Klein-Gordon equation for the scalar field. So this theory contains all the stationary solutions of GR, okay, and these solutions correspond to the case when psi is constant, psi naught, so for some constant psi naught. And if we linearize the equations of motions around this psi naught, you can take it as being 0, okay? We obtain the ordinary Einstein-Maxwell equations together with the Klein-Gordon equation for the scalar field perturbation, which I denote here as delta psi on the right, okay? So that's our linearized Klein-Gordon equation. And this system describes the linear or zero back reaction limit of the theory. So it's the limit in which the metric or the back reaction of both the metric and the electromagnetic field to a non-constant scalar field is or can be neglected, okay? So this framework, this linearization allows us to solve the Klein-Gordon equation for a known solution, a known GR solution of the Einstein-Maxwell equations, okay? So here we want to solve precisely this equation for a scalar field perturbation on the background of the Reissner-Nordstrom-Melvin black hole. And a tentative approach to this problem, which is not that complicated actually, is to use multiplicative separation of variables in this form, where here we have this dependence on t exponential, or yes, a complex exponential dependence on time. We have this omega, which is the frequency or phase angular velocity of the field. R and S are the radial and angular functions, respectively. And M, again, is the azimuthal harmonic index. So this ansatz, however, does not separate the Klein-Gordon equation unless we neglect terms of order higher than B naught squared, okay? But we can do that because we have assumed that this B naught is much weaker than BC. So this is a good approximation in this framework. So doing that, if we neglect those terms, the Klein-Gordon equation reduces to a radial equation and angular equation, so two differential equations. These are confluent Hoyne equations, and they are coupled through the Killing eigenvalues omega and m. So we have these two Killing eigenvalues that follow from the fact that the spacetime is stationary, okay? And they are also coupled through the mass m, the charge q, the magnetic field B naught, and this separation constant lambda, okay? Note that when this product m, little m times q times B naught is 0, we get, or the angular equation reduces to the standard or the general Legendre equation. And we know the solutions for that equation they are the associated Legendre polynomials of degree L and order m, okay? So the angular dependence of psi, of delta psi, is approximately described by the scalar spherical harmonics, okay? And we'll assume that's the case as well. So the radial equation, so the first equation we had before, can be cast as usual in a Schrödinger-like form by introducing the so-called tortoise coordinate. I think you are familiar with it. Here I call it epsilon, okay? And by introducing this new radial function, rho, so these definitions yield a rather lengthy expression for the potential V. So I'll omit that expression here. But anyway, the potential has this limiting behavior that you can see below. So as you can see, the effective potential tends to the square of little m times b naught squared. Okay, and this suggests that the magnetic field provides or gives the scalar field an effective mass. Okay, which is precisely given by the absolute value of little m times b naught. But here it is important to remark that this problem is not equivalent to that of a massive scalar field on an asymptotically flat stationary spacetime, because in that case, the mass of the field, the bare mass of the field, dominates the asymptotic behavior of the field. But here, the magnetic field, besides providing the field an effective mass, it changes the asymptotic behavior at infinity, right? That's why this solution is not asymptotically flat. It actually has some similarities with ADS asymptotics in the sense that it is naturally confining. Okay, so the magnetic field, the presence of the magnetic field leads to a confinement. So let me just, before proceeding, let me just explain this plot. So it shows the effective potential as a function of the radial coordinate r for different negative electric charges, right, per unit mass, so different charges to mass ratios. So from this plot, you can see that the magnetic field is like a potential barrier at r times b naught of the order of unity. Okay, so you can see, let me just point, you can see here that there is a potential barrier here, right, when r times b naught is approximately 1. Okay, and you can also see in the inset that the maximum of the potential approaches the event horizon when we increase in absolute value the charge to mass ratio. Okay. So this effective potential, in a sense, resembles a reflecting surface, a mirror, placed at some constant value r, and it confines low frequency scalar field perturbations in the black hole's vicinity. So it is natural to impose a Robin boundary condition at some r naught, r equal r naught, where r naught is of the order of the inverse of b naught, right? So that we can how can I say it? We can respect the threshold value for B. Okay. So here I have the expression for the Robin boundary condition. This theta parameterizes the Robin boundary condition. So if it's equal to 0, you get a Dirichlet boundary condition. I think you are familiar with that type of boundary conditions. And if it is equal to pi over 2, you get a Neumann boundary condition. Okay. But this is the general form of a Robin boundary condition or mixed boundary condition. On the other hand, the inner boundary condition, so the boundary condition at the event horizon, okay, is, as you can see, is a wave falling into the black hole when omega is greater than m times omega h, and is a wave emanating from the black hole when the reverse happens. okay? But again, something special happens when these two sides of the inequalities match. So when omega is equal to little m times capital omega h. So when this synchronization condition holds, the radial function no longer behaves as a wave near the event horizon, and bound states can form for particular values of the mass and the charge of the black hole. So note that this is just a detail. So if we assume that omega and B naught are positive, then the product of small m times q must be negative. Okay, that is why I just plot the effective potential for negative charge to mass ratios. Okay, and this synchronization condition happens in one-dimensional subsets. You will see this in a bit, in one-dimensional subsets of the two-dimensional parameter space of these black holes, and they are described by the mass and the charge. Okay, we'll see this in a bit. So let me just comment on the ways of getting these stationary clouds. So these stationary clouds can be found by solving the radial and the angular equations, and we can do that semi-analytically or numerically. Okay, we just need to solve either analytically or numerically an eigenvalue problem. Okay, analytically, for instance, this can be done using the this matched asymptotic expansion method. Okay, I mean, so we construct approximations to the solutions in the near horizon region and in the asymptotic region, and then we match them in the overlap region. Okay, and doing that, we obtain this condition on the left for the existence of these stationary clouds. And this, you can show that this condition is only valid when these, I think it's called VAR-P, I'm not sure, but anyway, it's only valid when this charge to mass ratio squared is greater than 16 over 25. Okay. And you can confirm this numerically. You only get solutions in that interval. Okay. Numerically, we perform a direct numerical integration using Mathematica. You don't need much more than Mathematica to perform such or to run such a code. It's very simple. And for that purpose, we write the radial function as a series expansion around the event horizon, and we integrate the radial equation from the event horizon to R0, to our boundary. Okay. And then we just use a shooting method to found, in this case, the values of the electric charge for which we get a Robin boundary condition at R equal R0. Okay. So let's look at the solutions. So here's the two-dimensional parameter space of these black holes. So they are characterized by the mass on the horizontal axis and the charge on the vertical axis. Okay, they are both normalized to the magnetic field strength. Okay, and the stationary clouds live precisely in that gray region, right? That gray region corresponds to the previous condition on the left in the red box, right? So stationary clouds can only appear in that gray region. Okay. So these bound states occur precisely, as I said previously, in these one-dimensional subsets of the parameter space. They correspond to these lines. Okay, they are known as existence lines. They are disjoint. Okay, and can be labeled using three quantum numbers. Okay, pretty much like an electron in a hydrogen atom. And those numbers are the number of nodes, so the number of nodes in the radial direction, n, the orbital angular momentum L, and the azimuthal harmonic index m. Okay, so this plot in particular shows the existence lines for stationary clouds with n equal to 0 and L equal to m equal to 1. And these particular solutions satisfy a Dirichlet boundary condition. And we have here a plot for different values of R naught times B naught. Okay. By the way, you get similar results for different Robin boundary conditions. I'll just present this example because they are very similar. Let me just comment, make a few comments about this plot. So you can see that for a fixed mass, so if you draw a vertical line, the absolute value of the charge increases as the size of the system, so R naught, decreases. And this is easy to understand. So as R naught decreases, the scalar field gets closer to the horizon. So the horizon must rotate faster so that it can support the cloud around it, okay? And this is achieved, so you achieve a faster rotation only if the electric charge of the black hole increases. And that's why the absolute value of Q increases as R naught decreases, okay? So to conclude, let me just run over some key points again. So if you consider a massless neutral scalar field interacting with a Reissner-Nordstrom black hole, okay? So we are talking about the system on the left. So this system is not prone to superradiance. It would be if the field was charged, okay? It's not the case, so we don't have superradiance in this case. And also, this system does not feature a natural confinement mechanism because the field is massless, we don't have a magnetic field, we don't have a mirror, so we don't have either superradiance nor a confinement mechanism. If this same system is immersed in a uniform magnetic field, the black hole starts spinning because it's charged, so it starts spinning. It acquires an ergo region and therefore becomes prone to superradiance. Okay, and on the other hand, the magnetic field provides a natural confinement mechanism. So for most, if not all, stationary clouds studied in the literature so far, these two ingredients, superradiance and the confinement mechanism, are usually added separately. Okay, but we showed that this is not necessarily the case. So this superradiance and confinement can have the same origin, in this case, the magnetic field. So thanks for your attention. If you have any questions you'd like to ask, I'll be happy to answer them.
Well, Nuno, thank you for your excellent presentation. And I'd like ask everybody to turn on their microphones for a round of applause in retribution to that.